Today's problem is an application of work-energy theorem. The problem is you are using a rope to lift a 14.5 kilogram crate of fruits. Initially, you're lifting the crate at zero point 0.5 meters per second. You then increase the tension in the rope to 175 newtons and lift the crate an additional 1.25 meters. During this 1.25 meter motion, how much work is done on the crate by letter A, the tension force, and letter B, the work done by the force of gravity, and letter C, the work done by the net force. The last question is what are the kinetic energy and speed of the crate after being lifted the additional 1.25 meters? Okay, what are the given quantities? So we have the mass of the crate, which is 14.5 kilograms. You also have the weight, which can actually be calculated by just multiplying the mass by acceleration due to gravity, and the weight that corresponds to 14.5 kilogram mass is 142 newtons. Then, as shown in the drawing, the tension force exerted by the rope is equal to 175 newtons directed upward. The initial speed of the crate V0 is equal to 0.5 meters per second, and the additional distance is equal to 1.25 meters. What are the unknown variables? We are asked to find the work done by the rope. Next, we also asked to find the work done by gravity, and then get the total work done by the net force. And lastly, the final kinetic energy of the crate as well as final speed of the crate. Now, to help us in our analysis, the vector diagram on your screen shows a crate that is denoted by a particle. Okay? Initially, the crate has an initial speed of 0.5 meters per second, that is denoted here by V0. At this initial position, we also have the kinetic energy initial, but that is still have to be calculated later on. Now, the two forces acting on the particle, which represents the crate, we have the tension, upward tension force, and the force of gravity, labeled here as small w, which actually is equal to mg. Then because the tension force of the rope is greater than the pull of gravity, the F net must be in the upward direction, and this is equal to tension force minus mg. So because of the net force directed upward, the crate will have to move upward through a distance d. Okay? And at that point, which you consider the final position, we are to determine the final speed as well as the final kinetic energy. Alright, so let us execute our equations that we are going to apply in getting the unknown variables. For the work done by the rope, we label it as capital W sub T. We just multiply the tension by the displacement. That is 175 newtons multiplied by 1.25 meters, and we get 219 joules as the work done by the rope. Okay. Next, for the work done by gravity, we simply multiply the mass by the acceleration due to gravity. That's in fact the weight of the crate, and if we multiply it by the displacement, then we are getting the work done by gravity. And that is equal to 14.5 kilogram multiplied by negative 9.8 meters per second squared, multiplying by 1.25 meters as the displacement. We get a negative work equals negative 178 joules. Why is this negative? Well, we know that the force of gravity is directed downwards, but the displacement of the crate is upward. So this is the result of getting the work done by gravity. We have a negative work done. Alright? So, what is next? We can then determine the total work done. Total work done is just the sum of the work done by the tension and the work done by gravity, or WT plus WG. So substituting, we have 219 joules plus negative 178 joules, and we get 41 joules. 41 joules, which is a positive work done. Okay? So, at this point, we can actually predict what's going to be the final kinetic energy of the crate. Since the work done by the net force is positive, okay, we can predict that the final kinetic energy of the crate is going to be greater than the initial kinetic energy. Okay, we will be able to find that out if our prediction is right in the succeeding computations. So we now proceed, and for us to calculate the final kinetic energy of the crate, we first have to find its initial kinetic energy using the formula 1/2 mv naught squared. Substituting the given mass and the given initial speed and doing your algebra, we find the value for the initial kinetic energy, which is 1.81 joules. Now, are we going to use the same formula for kinetic energy to find the final kinetic energy? The answer is no. For this tutorial, we are not going to use this formula since we don't know the final speed v. Okay? We can actually determine the final speed. If you recall, we have a formula in kinematics which says that final speed, or the square of the final speed, is equal to the square of the initial speed plus 2 times acceleration times the displacement. But then again, in this particular formula, we don't know the acceleration either. Alright? We don't know the acceleration. We don't know the final speed. We know only the initial speed and the displacement. So two unknown variables in one equation, we can't proceed. But Newton's law of acceleration will give us the way to find the acceleration. Simply divide the net force, which anyway has been determined, and the given mass m. But the emphasis of today's tutorial is to use and apply a special equation that involves the relationship between work done and kinetic energy. We call this the work energy theorem. Alright, so the formula goes like this. W net is equal to delta K, which is equal to final kinetic energy minus initial kinetic energy. Okay, we can use this in this situation because the object that we are considering here is moving in a straight line path. So it moves as the object moves from the initial position here, it goes to the higher position. All right, and because of that, this is the equivalent formula for finding or for relating the work done and the change in kinetic energy. But since we're looking for K, or the final kinetic energy, we simply isolate K and get this working equation. So we can substitute, since we know already the value of the work done by the net force, which is 41 joules, and then the value of the initial kinetic energy, which we have just calculated here. All right, and we add 41 joules plus 1.81 joules to get, all right, the value for the final kinetic energy, and that is 43 joules. So from here, we can now proceed to find the value of the final speed v. We just isolate the v, put it in one side of the equation, and we have the working equation, which is final speed is equal to the square root of twice the kinetic energy divided by the mass m. And if we substitute, we have square root of 2 multiplied by 43 joules, and then divide the whole thing by 14.5 kilograms. And we will get square root of 34. With the help of your calculator, we can now find the final speed v, and that is 5.8 meters per second. All right, so we are done with our computations, and we can now make our conclusion. That is, if the total work done on a body appears to be positive, it means that the change in kinetic energy of the object will also be positive, and the change in speed will also be positive. In other words, because of the work done by the net force on the crate in moving it upward from the initial position to the final position through a displacement of 1.5 or 1.25 meters, the body's kinetic energy has increased, all right, from 1.81 joules to 43 joules. So there is really a great amount of delta K acquired by the crate. So just to check our working equation of the work energy theorem, it says here that the net force W net is equal to K minus K naught. Our value for K is 43 joules. All right. If you subtract from that value 43 joules, the amount of initial kinetic energy, which is 1.81 joules, we will get as the value of the work done, which is 41 joules rounded to its whole number. Alright, so that checks our computation. Alright, so we are done. Thank you very much for watching. Don't forget to subscribe.